Hey, Harsh here. In the model application development, specifically where we look at skills required, and nowadays the database persistence layer inevitably becomes the performance bottleneck. We are talking about systems generating insane amount of data and handling thousands and millions of concurrent transactions. At this scale, vertical scaling, simply adding more RAM or CPU into a single machine, hits a hard physical limit. To go further, we need architectural distribution. This brings us to partitioning and sharding. While both involve dividing table into smaller pieces, they address completely different scaling problems. Confusing them is a classic mistake. Although they are related, sharding and partitioning are fundamentally different architectural strategies. Partitioning is an internal optimization technique. Think of it as taking a huge heavy monolithic box and installing internal dividers in it. The contents are now logically segmented into smaller pieces or partitions, but that box is still a single physical server. The primary motivation here is improved performance, especially through a technique called partition pruning, where the query optimizer knows to exclude irrelevant partitions from a scan, significantly reducing the I/O required. Sharding, on the other hand, is an architectural commitment to scaling out. It's taking that massive box and breaking into, say, smaller boxes, each placed on its own independent physical machine or a shard. Each shard is a complete autonomous database instance holding on a unique subset of total data. This is pure horizontal scaling. When a single server runs out of I/O, CPU throughput, and storage volume, sharding is necessary next step to distribute load and scale capacity almost linearly with every machine needed. The crucial implementation is complexity. Partitioning is managed natively by DVMS, while sharding requires network coordination and complex management. Partitioning is designed to manage tables to grow to billions of rows. One of the most common reasons to partition is simply to make administration easier. When managing a massive table, tasks like rebuilding an index or running backups become resource intensive and time consuming. By splitting a huge table into, say, 12 smaller monthly partitions, you can manage 12 smaller pieces individually. For queries, partitioning provides a crucial boost through partition pruning. For example, if you have a sales table partitioned by year and a query sales for 2024, the query optimizer immediately knows to skip partitions 2023, 2022, and the prior years. This significantly reduces the amount of data the system has to scan, leading to faster query response times. Partitioning is especially valuable for large structured datasets common in finance, IoT, healthcare, and applications frequent on time-based queries. The fundamental goal is localized performance gain and administrative agility. When partitioning horizontally, dividing table by rows, we have several core strategies depending on our data and query patterns. First, we have range partitioning. It is the most common technique, especially for all time series and logging data. You define partition boundaries based on continuous values. For example, creating a partition sales underscore 1999 for all the dates before January 1, 2000. A powerful extension is interval partitioning, where once you define the first range partition, the database automatically creates subsequent partitions based on specified interval, say monthly or yearly, when a new data arrives. This means less manual overhead as time passes. Next is list partitioning, where you explicitly define a set of discrete values that belong to a partition. If we partition sales data by channel ID, we might put channels 2 and 4 into even channels and 3 and 9 into odd channels. This is great for categorical data where the grouping isn't numerical or sequential. Finally, hash partitioning is used when you simply want to distribute data evenly as possible to avoid hotspots. The database applies an internal hash function to a key like prod ID, and the result determines the partition. This is simple and effective for balancing load, especially when using a number of partitions that is a power of 2. For maximum flexibility, we often use composite partitioning, when we partition by one method and then sub-partition each result by a second method. For example, partitioning by the year and then subdividing that year's data by a state. While horizontal partitioning focuses on splitting rows, vertical partitioning focuses on splitting columns. The goal here is usually performance optimization by making commonly accessed data blocks smaller, improve caching, and reducing retrieval speed for common queries. Think of wide products table that has core data like name and price, but also massive, rarely accessed fields like images and review summaries. Vertical partitioning splits this into separate tables, say product score and products media. Now, a query for just product table doesn't have to scan past the huge image fields. This is also useful for security, restricting access to sensitive columns like passwords, or salary information. A specialized technique in relational databases, particularly Oracle, is reference partitioning. This is extremely elegant. The partitioning of a child table is automatically derived solely through a foreign key relationship in the parent table. For every partition in the parent table, an exact corresponding partition key exists in child table. This ensures that when querying data like orders, which is the parent table, and order items, which is the child table, the related records reside in the same physical partitions, streamlining operations. We also have partitioned indexes. Local partitioned indexes are automatically linked to the table's partitioning method, simplifying maintenance because if you move a table partition, only the associated local index partition needs rebuilding. In contrast, global indexes are partitioned independently. When do you choose partitioning? It is a go-to strategy when your monolithic database is struggling internally but has not yet hit the absolute physical limits of a single server hardware. The core benefit, as discussed, is partition pruning. For instance, a healthcare database partitioned by patient age can return records for patient within a specific age range much faster by only scanning the relevant partition. This boosts the efficiency by querying time series data or data defined by categories. The administrative benefits are equally huge. Imagine a team managing transaction logs. If they partition by month, deleting 2022's data in 2025 doesn't require a slow row by row delete operation, which can be disastrous on a hot table. Instead, they simply drop the old partition, which is an instantaneous metadata operation, saving significant resources and risk. Partitioning is the prerequisite, the essential database administration and optimization strategy that should be implemented first. It pushes the boundary of a single server, often delaying the complex and costly jump to sharding. Once you have hit the limits of what even the most optimized single server can handle, perhaps hundreds of millions of users or high volume write traffic, you must scale out. This is where sharding comes in. Sharding is taking your gigantic database and splitting its rows across multiple independent physical machines. Each server or shard is fully autonomous database instance responsible only for its unique subset of data. This distributed design is also known as shared nothing architecture, which means adding new shards adds capacity almost linearly because there is minimal coordination overhead. The entire mechanism pivots on the shard key. This key comes from a column like customer ID or order ID and is the guiding map that determines exactly which physical server stores that row. When a query comes in, a dedicated software layer, whether it's a middleware or a proxy or built-in logic in a distributed database, reads the shard key and routes request directly to the correct code. This parallelism across multiple servers is what gives sharding its scaling power. The choice of shard key is arguably the single most critical decision in distributed system design. A bad shard key leads to an imbalanced cluster with performance killing hotspots. A good key must have high cardinality. If you choose a field like region that has only 5 values, you are immediately limited to 5 potential shards. A user ID, by contrast, provides high cardinality, allowing for much finer distribution. Second, it must provide uniform data distribution. This is where the concept of monotonic change comes in. If we shard by a simple auto-incrementing ID or a timestamp, all new write traffic, which is usually the heaviest load, will continuously hammer the single same shard, making it a hotspot and defeating the purpose of sharding. For write-heavy systems, keys must maximize load uniformity, often by combining timestamps with random events or hashed keys. Third, the key must align with your primary query patterns. If your application frequently queries by customer ID, making customer ID the shard key ensures that queries hit only one shard. Choosing shard key is only half of the battle. We also need a strategy to apply that key. We basically have 4 dominant methods in this area. Range-based sharding is intuitive. If you shard by customer name, A to I goes in shard 1, J to S goes in shard 2, and so on. The advantage is obvious. Localized operations are fast as range queries like retrieving all transactions from last month hit a single node. The major weakness, as seen in customer name example, is that the distribution may be highly uneven, leading to hotspots where shard 1 handles far more load than shard 3. Hash-based sharding, using a mathematical hash function on the key to scatter the data evenly across shard. This ensures excellent load balancing for high volume writes. The trade-off is losing data locality. Consecutive IDs are scattered randomly. This makes range queries resource intensive, often requiring a scatter gather query across all shards. MongoDB, for instance, offers hash sharding. Directory-based sharding is the most flexible. It decouples the shard key from the physical location via a lookup table or a shard map. To move data, you only update the map, not the hashing logic. The downside, the lookup service becomes a mission critical single point of failure or a latency bottleneck. And then we have geo sharding, sometimes referred as tag sharding, splits data by geography to meet latency goals and data sovereignty requirements, ensuring that all EU data stays on EU servers, for example. It's crucial not to confuse sharding with replication. They are complementary techniques that solve different problems. Replication is about creating redundancy. It makes exact copy of data across multiple machines. This is primarily used to increase read capacity by distributing read requests across read replicas and to provide high availability. If primary database fails, a replica can instantly take over. Replication duplicates the data. Sharding is about partitioning the data set itself. It does not create copies of the same information, rather it spreads unique subsets of data across different machines. This solves the problem of a single machine maxing out its write capacity or storage volume. In highly resilient systems, you use both. You shard the data horizontally across multiple servers, P1, P2, P3, to handle scale, and then for each of those primary shards, you deploy a replica R1, R2, R3 for fault tolerance and read offloading. This way, if P1 crashes, R1 is promoted instantly to keep that portion of dataset available. This is known as a sharded cluster with replication offering both scale and high availability. The issue is consistency. In a single monolith database, a transaction is easy. In a sharded system, if a money transfer requires deducting funds on shard A and then adding them to shard B, both must succeed or fail atomically. The classic solution for guaranteeing this atomicity is two-phase commit or 2PC. Protocol uses a coordinator node and multiple participant shards. A phase 1 is preparation, and the coordinator asks all the shards if they are ready to commit and lock resources. If everyone says yes, we move to phase 2, where the coordinator issues the final commit command. While 2PC ensures strong consistency, its cost is immense. It's a synchronous blocking protocol. If the coordinator fails or if one shard stalls during commitment phase, the whole transaction is delayed or halted, compromising availability and dramatically lowering write throughput. This high penalty often means high volume architectures actively design their systems to avoid cross-shard transactions entirely. This is why systems like Apache Sharding Sphere support distributed transaction protocols like 2PC and Base. Since cross-shard operations are the Achilles heel for distributed databases, proactive design is essential. The goal is simple: minimize cross-shard dependencies. The most powerful technique is data coalition, also known as affinity sharding. You must ensure all tables frequently joined together use the same shard key. For a gym tracker, if the huge exercise log table is sharded by user ID, the much smaller users table must also be sharded by user ID. This guarantees when a user logs in and requests their workout history, the query only needs to access a single shard, a fast local join instead of network intensive distributed joins. For very small static tables that are required globally, like product catalog or a list of exercises, the best strategy is often to use a reference table. This means replicating a full copy of the small table onto every shard. This eliminates cross-shard queries for common lookups, provided the reference table doesn't update frequently, as every change will require synchronous updates across all the replicas. Sharding isn't a one-time decision. Your scale needs to evolve, forcing you to change your topology. This is called resharding. If one shard becomes overloaded, a hotspot, you need to split it into two shards or rebalance chunks of data to other quieter nodes. Traditionally, this meant lengthy offline migration. You take the data out of service, move the petabytes of data, verify consistency, and then bring it back online, which is costly in terms of downtime. Most systems have zero downtime or online migration capabilities. They start a process called double writing. Write new data to old and new shards simultaneously, migrate all historical data in the background, and then perform an atomic switchover with minimal disruption. This atomic data movement is crucial because manually managing distributed data movement is an enormous operational risk. The ability to scale out by adding nodes at runtime without downtime is significant modern benefit of systems built for distribution. For greenfield projects or extreme scale requirements, many developers turn to databases where sharding is core, native capability simplifying operational overhead. In the NoSQL world, we have MongoDB, which natively supports sharding. You define a shard key and its route to service. Mongoose handles the distribution of the data, managing chunks and balancing load across the cluster automatically. Apache Cassandra takes distribution even further. It's a masterclass peer-to-peer system where data distribution is inherent to the design. Data is automatically partitioned across the clustering using consistent hashing, providing high availability and resilience without the need of external hardware. Bridging the gap between is NewSQL. Databases like CockroachDB and DIDB, these are designed to offer more expressive power and relational integrity of SQL, plus the horizontal scalability of distributed systems. They handle all the complex logistics like sharding logic, data distribution, and maintaining consistency, often using Raft or other similar protocols behind the scenes. To the developer, it looks like a one massive Postgres or MySQL instance, but it can be scaled globally with just simply adding nodes. The final decision is yours. You must strategically determine if you need to optimize within your current hardware limits or you need to buy more physical resources. If you're struggling with massive unwindly tables, say over 2 gigabytes, but your server has still headroom, the solution is partitioning. This is low complexity, high reward, focusing on performance, pruning, and administrative manageability. If you are hitting the absolute physical ceiling, CPU is saturated, IO is maxed out, or you have extreme write throughput demands, you must use sharding. This is a high complexity, high cost solution, but it grants you virtually limitless horizontal capacity and superior fault isolation across machines. Remember, sharding is complex, requiring advanced management for cross-shard joins and data consistency. Never introduce sharding prematurely. It's a commitment to distributed complexity.